You can use your right hand as follows to determine the direction of the magnetic field relative to the current. Imagine grasping the wire with your right hand, with your thumb pointing in the direction of the current. Your remaining fingers will circle the wire, giving you the direction of the magnetic field. This is known as the second right-hand rule. Once you have found the direction of the magnetic field relative to the current, you can use the right-hand rule to determine the direction of the magnetic force acting on the wire. Which way is the current in the wire traveling if the magnetic field is directed out of the screen?
Correct.
We can see that the magnetic field that is created when current flows through a long straight wire are represented by circles around the wire. How does the magnetic field strength vary with the strength of the current I in the wire and the distance r from the wire? The concentric rings showing the magnetic field get weaker with increasing distance from the wire. With double the distance from the wire, the magnetic field strength is half as strong. Therefore, we can deduce that the magnetic field strength is inversely proportional to the distance from the wire. But near the ends of a long wire, the magnetic force is no longer inversely proportional to the distance from the wire because of distortions to the symmetry of the field. The field strength is inversely proportional to the distance as long as the distance from the wire is less than the distance to an end of the wire. Another generalization that can be made is that, when the current flowing in the wire increases, the magnetic field strength also increases. In fact, the magnetic field is directly proportional to the strength of the current in the wire. From these generalizations, we can conclude that the magnetic field B is directly proportional to the current I and inversely proportional to the distance r from the wire, which can be written B is proportional to I divided by R. But remember, this relation holds only when the distance from the wire is less than the distance to the ends of the wire. To make this relation an equation, a proportionality constant K must be added. The proportionality constant K equals mu sub 0 divided by 2 times pi. The mu sub 0 is called the permeability of free space and is equal to 4 pi times 10 to the negative 7th Tesla meters per amperes. The formula becomes mu sub 0 divided by 2 pi times the quantity current divided by the distance from the wire. This is equal to 2 times 10 to the negative 7th Tesla meters divided by amperes times the quantity I divided by R. The accuracy of a magnetic compass in an airplane is affected by magnetic fields that are generated nearby. What is the strength and direction of the magnetic field created as indicated by a compass by a wire that is 1.0 centimeters behind the compass and carrying 1.5 amperes of current? How would a clever aircraft engineer design a system to cancel out the magnetic fields around the compass? Using the right-hand rule, we can show that the magnetism produced by a second wire will cancel out the magnetism produced by the first wire. Therefore, the engineer could add a second current-carrying wire positioned at the appropriate distance from the compass and having the same strength and current direction as the first wire. Doing this would cancel the magnetic field around the compass. This is called the principle of superposition. Assume you have two parallel wires 10 centimeters apart. The wire on the left, A, carries 5.0 amperes, and the wire on the right, B, carries 4.0 amperes. What is the strength of the magnetic field at a point 3 centimeters from the left wire and 7 centimeters from the right wire?
Correct.
When placed in the magnetic field, a wire experiences a force. This is also true for two current-carrying wires. In addition, when two current-carrying wires are placed in a magnetic field, they exert a force on each other. Let's use the first right-hand rule to find the direction of the forces on the wires. Using your right hand, point your index finger in the direction of the current, your middle finger at 90 degrees to your palm in the direction of the magnetic field. Now your thumb is pointing in the direction of the force. What is the force FA on wire A caused by the wire B? The force on wire A caused by the magnetic field from wire B equals the current in A times the length of A times the magnetic field strength of B at wire A. The magnetic field strength of B equals the permeability of free space times the current in wire B, all divided by 2 pi r. Let's divide both sides of the length L to get the force per length and then substitute in the numerical values of the constants. The force per length, then, equals 2 times 10 to the negative 7th meters per amperes times the product of the two currents, all divided by the distance between the wires. What about the force on wire B, FB? We use the same reasoning as that for the force on wire A, and find that force per unit length on wire A equals the force per unit length on wire B. The forces T we are talking about could be repulsion or attraction forces. When the currents are moving in the same direction, then, as you can see, the wires attract one another. However, if we reverse the current direction in one of the wires, then the currents are the opposites of each other, and the wires will repel each other. Parallel wires repel each other when their currents are moving in opposite directions, and, as we just saw, attract each other when their currents are moving in the same direction. What is the force per length between two wires that are 50 centimeters apart if one is carrying 10 amperes of current directed out of the screen and the other is carrying 15 amperes of current directed into the screen?
Try again. Try again. Correct.